There are quite different methods for starting an electric motor, such as direct online or DOL, star delta, auto transformer, primary resistor, or using solid-state power electronic devices, such as VFD or soft starter. Every single method has its own specific applications and benefits. In this lesson, we are going to discuss the soft starter method amongst all, and we will cover the rest of the methods in future videos. Since electric motors often require large amounts of electricity during their accelerating to the nominal speed, a soft starter can be used to limit the surge of current, known as inrush current, and torque of the electric motors, resulting in a safer, smoother, and gradual startup. Soft starters will protect your electric motor from possible damage, and at the same time extend the lifespan of your electric motor and the whole system by declining the heating caused by frequent start-stops, reducing the mechanical stress on the motor, its shaft, and reducing the electrodynamic stresses on the power cables. Large inrush current also places a high demand on the electrical supply system, which results in extra cost. Soft starters are commonly used in industrial applications that have a high inertia load that requires a large inrush of current. One example of this is an air scrubber or dust collector. These will have large fans inside. In this application, it will take some time to get the fan moving, but once the fan is moving, the current and torque load on the motor is reduced. In the system, the fan will pull air into the filters where dust particles are collected. Then the clean air is pushed back to the factory. Water supply applications are another great use for soft starters. When using pumps in a process, you have to bring them up slowly. If not, you'll cause pressure surges in the water system that could lead to dangerous conditions. Conveyor systems that move heavy loads can be maximized by using a soft starter as well. A soft starter will be located inside the control panel and will be supplied with three-phase power on the top. Then on the bottom, the soft starter will supply three-phase power out to the motor. The soft starter can be controlled either by a direct start-stop wiring, or it can be controlled over Ethernet. Both control methods have their advantages and disadvantages. Direct start-stop signals would not require a PLC. They would be less expensive. Using Ethernet control, a PLC is required. This will allow there to be feedback, which will give adjustable control and monitoring capabilities. Now that we've talked about some applications and how the soft starter is wired into a system, let's dive into the internal workings of the soft starter. The main component of a soft starter is a triac, which is designed to limit the applied voltage to the motor. Triac consists of two back-to-back thyristors, or SCRs. When an internal pulse is applied to its gate, it allows current to flow, which then sends current out to our motor. The pulses are sent based on ramp time, so the current will be slowly applied to the motor. This will allow our motor to start slowly, reducing torque and inrush current. When the motor reaches full speed, the soft starter and DOL work the same. The difference is how they act while getting to full speed. When comparing the voltage between a DOL starter versus a soft starter, we can see that there is a direct inrush of voltage on the DOL, where the soft starter takes more time to get up to full voltage. The current is more regulated using a soft starter. With a DOL, there will be larger spikes in current as the motor starts. With a soft starter, the time the motor gets us to speed is slower and more controlled, while a DOL gets the motor up to speed almost instantly. This can have undesirable effects that we will talk about next. The torque applied to the motor as speed increases is greater when using a DOL, opposed to a gradual torque increase using a soft starter. Now that we know what a soft starter is and how it works, let's go back to our industrial applications and apply what we know on why a soft starter can prevent undesirable mechanical and electrical effects. When a DOL is used in these applications, there will be a sudden impact at startup on the load, along with a rapid acceleration, which causes excessive wear. Our air scrubber fan will be driven by a motor using belts and pulleys. Using a DOL can cause the belts to slip and wear. With our water supply example, the DOL will cause pressure surges on the water lines. This can cause excessive wear, which could lead to line breaks. And our last application is the conveyor system. DOLs will cause strain on the components that drive the conveyors, along with the couplings and bearings. These undesirable mechanical effects can lead to continuous maintenance, unscheduled shutdowns, and shorter component life. There are also electrical effects that we want to avoid by using a soft starter. The heavy current surges that a DOL can cause can burn out contacts and motors. In conclusion, when an industrial application has a high inertia load that will require a large inrush of current, a soft starter is an ideal option for controlling the system. Also, we talked about the wiring and control of the soft starter, as well as the internal components, and how triacs control voltage to the motor based on ramp time.